Welcome, my friends! In this video, we will be calculating the least squares linear regression line, first by hand, and then using the TI-84 calculator. I introduced scatter plots, correlation, and linear regression in my previous video linked in the description, and I encourage you to watch that one first, especially if you are unfamiliar with the correlation coefficient R. As a brief review, a scatter plot graphs the relationship between two related variables, x, which we call the independent or explanatory variable, and y, the dependent or response variable. Our goal is to find the straight line that fits the dots the best. By best, we mean the line that has the smallest squared vertical distance from each point to the line. We call this line the least squares line, and linear regression helps us determine the equation of the line. The least squares regression equation has the form y hat equals a plus bx. Y hat is the predicted value for y based on the least squares equation. A is the y-intercept and represents where the line will intersect the y-axis. B is the slope and represents how much y is predicted to increase for a 1-unit increase in x. X is the independent variable that will be used to predict y. The reason that we have y hat instead of y is because the least squares line isn't perfect. We use the equation to predict y, and we call our prediction y hat, but our prediction will usually be a little bit off, which is why all the dots on a scatter plot do not fall exactly on the least squares line. Now, in order to find the equation of the line by hand, we need to find three quantities. First, we calculate the correlation coefficient R using this formula. There are ways to find the equation of the line by hand without first finding R, but finding R makes the slope equation simpler, and it's nice to know how to calculate R anyways. Then we calculate the slope, B, using this formula, which requires us to know the correlation coefficient R. Finally, we calculate the y-intercept using this formula, which requires us to know the slope, B. There are alternative formulas for some of these values, but these are the versions we will be using in this video. We don't need a formula to find x, as x represents the observed data that will be used to predict values of y once we've created the equation. Let's take a look at an example. Listed are the age in years and weight in pounds of 8 males, ranging anywhere from age 3 to age 18. The scatter plot of the data shows a strong positive correlation. As age increases, weight also tends to increase, and a straight line fits the data quite well. Let's begin by calculating the correlation coefficient R using this formula. Now, I'm going to cheat just a tiny bit by finding the sample means, x bar and y bar, as well as the sample standard deviations, sx and sy, on my TI-84 calculator. I have other videos where I calculate the mean and standard deviation by hand, so check out those videos if you'd like to see them. On the TI-84 calculator, press Stat, enter for edit, and clear list 1 and 2 by pressing clear while hovering over whichever list you want to clear, and then pressing the down arrow. I'm not going to clear my list since I already have the data entered in. Now press Stat, arrow over to Calculate, scroll down to 2 variable statistics, and press enter. Make sure you have list 1 and list 2 as the x and y lists. Press second 1 for list 1 and second 2 for list 2 if you need them. Leave the frequency list empty and press enter with calculate selected. On a TI-83 calculator, you won't get that previous menu, and you can just press 2 var stats and you should get the same results that I have here. Now let's copy down the important information that we need in order to calculate R, which is x bar, y bar, sx, sy, and n. X bar is 10, sx is 5.529, and ideally we would include more decimal places, but I'm fine with rounding to 3 to simplify the calculations. Follow the rounding conventions of your instructor. N is the sample size of 8, and scrolling down, we see that y bar is 81, and the standard deviation of y is 49.679. Now if we take a look at the formula for R, we see that the biggest challenge is the numerator, the sum of x minus x bar times y minus y bar. The easiest way to calculate the numerator is to extend the table the data was given in so that there are 3 additional columns. In the first column, we take each x value or age and subtract the mean of x of 10. we get 3 minus 10, which is negative 7, 4 minus 10, which is negative 6, 7 minus 10, which is negative 3, etc. We do the same thing for y. Take each y value, or weight, and subtract the mean of 81. 27 minus 81 is negative 54, 38 minus 81 is negative 43, etc. If you'd like to check your work up to this point, you can add up the two columns that we just calculated, and you should get 0 for each of them. For the final column, we simply take the x minus x bar column and multiply by the corresponding value in the y minus y bar column. When we do that, we get this result. Negative 7 times negative 54 is 378, negative 6 times negative 43 is 258, etc. Now, since the formula has the summation sign in the numerator, we need to add up all of the x minus x bar times y minus y bar results, which is the column we just finished making. If we add up all of those values, we get 1,887, which is the numerator of the formula for r. The denominator consists of all numbers that we know, n minus 1, or 8 minus 1, times the standard deviation of x of 5.529, times the standard deviation of y, which is 49.679. Here is the result. Type the result into the calculator like this, and you should get 0.9814. Remember that r ranges from negative 1 to 1, and values close to 1, like 0.9814, represent a strong positive correlation, meaning that as x increases, y tends to increase as well. As a side note, if you square this number, you get 0.9631, which is a number we often call the coefficient of determination, and tells us that 96.31% of the variation in y is explained by x. Or in this case, that 96.31% of the variation in weight can be predicted by age. Not too bad. Okay, let's move on to calculating the slope and the y-intercept. For the slope, b, the formula is r times the standard deviation of y over the standard deviation of x. We have 0.9814 times 49.679 over 5.529, which equals 8.818, rounded to 3 decimal places. The y-intercept a is equal to y bar minus b times x bar, or 81 minus 8.818 times 10, which is equal to negative 7.18. Recall that the equation of the least squares line is y hat equals a plus bx. Our equation becomes y hat equals negative 7.18 plus 8.818x. This is the equation of the line that best fits the points from the scatter plot that we looked at earlier. Now, there are two main things that this equation is used for. One is to interpret the slope, which is the coefficient on x of 8.818. In general, the interpretation of the slope is that, for a 1 unit increase in x, y is predicted to increase by whatever the slope is. In our case, x is age and y is weight in pounds. So the interpretation of the slope is, for a 1 year increase in age, the weight of a male child is predicted to increase by 8.818 pounds. The other main use of this equation is to make predictions for y using values of x. So for example, our initial dataset did not contain any male children aged 12, so we might plug in x equals 12 into the equation in order to predict the 12-year-old's weight. We have y hat equals negative 7.18 plus 8.818 times 12, which simplifies to 98.636. We predict that a 12-year-old male will weigh about 99 pounds. Let's try another one. What if we had a male that was 38 years old? How heavy would our model predict this individual to be? Well, we have y hat equals negative 7.18 plus 8.818 times 38, which simplifies to 327.904. We predict that a 38-year-old male will weigh about 328 pounds. Something doesn't seem right here. I wonder if you can put your finger on it. Most 38-year-olds are not 328 pounds. Remember that our dataset was made up of children from the age of 3 to 18. We are now using the model to try to predict the weight of someone aged 38, way outside of the range of ages used to build the model. In general, when we try to make predictions for y using values for x outside of the range of the initial dataset, we call that extrapolation. The predictions made using extrapolation should be evaluated with caution, as they will oftentimes be inaccurate. On the other hand, when we try to make predictions for y using values of x that are within the range of the initial dataset, such as when we predicted the weight of a 12-year-old earlier, we call that interpolation. Predictions made using interpolation will generally be more accurate than predictions made using extrapolation. Okay, to wrap things up, let me quickly show you how to get the least squares equation using the TI-84 calculator. Earlier, I had you enter the data into the stat list, which you can access by pressing stat and then enter. So if you haven't already entered the data, do that now. Next, press stat again and arrow over to calculate. Scroll down to option 8, which is linreg a plus bx. You'll notice option 4 is also linear regression, but in the form ax plus b. You will get the same answer using option 4 or 8, but option 8 matches the form of the equation we have been using, so that's the one that I will use here. Press enter, and you will be prompted to enter the x and y lists. If the lists don't already say L1 and L2, press second, 1, enter, second, 2 to change the lists. Leave the frequency list and store reg EQ blank and press enter over calculate. And there you have it. We have the y-intercept A and the slope B, which match our calculations from before. We also have r and r squared. If your calculator settings are not correctly configured, you won't get r or r squared. To correct for this, press second, 0 to get to the catalog, then press x to the -1 power, which is standing in for the letter D. Scroll down until you see diagnostic on. Press enter and enter one more time, and the calculator will say done. Now, next time you run linear regression, you should get the r and r squared values. Alright, my friends, that wraps up our discussion of linear regression. We will be exploring many more fun and exciting statistical topics that you won't want to miss, so make sure to check out our other videos.